Hello, in this video I will show you how to run a log linear model in SPSS, also how to interpret result of log linear model for models that involve more than 3 variables. Here on the screen you see that we are in SPSS and we have this dataset that has 4 variables. This dataset is called Titanic, and 4 variables are uh, a class, sex, age, and survived. Now let's take a look at what each level of these variables are. First variable class has 4 levels. Level 1 is basically passengers from the first class. Level 2, uh, passengers from second class. Level 3 from third class, and level 4 are the crews. Second variable sex have 2 levels. Level 1 is male, level 2 female. Third variable age also have 2 levels. Level 1 is child, level 2 is adult. And the last variable survival also has 2 levels. Level 1 is no, those passengers who did not survive, and level 2 is yes, those who have survived. Now let's first weight our variables by using the frequency. Go to data, weight cases, and weight cases by frequencies. And okay, now we can go to select our log linear model. Go to analyze log linear model selections. We select all 4 variables into the window of factors. Let's first define the level of different variables. For sex, age, and survived, all these variables has only 2 levels. The minimum is 1, maximum is 2. So we can define them all together. For the variable class, it has 4 variables. The minimum is 1 and the highest level is 4. So we defined the range of these 4 variables. Let's go to a model. So we can start from saturated models because we want to select uh, the best possible model and those terms that will remain within the model. So we like to start with a saturated model. Okay. Then let's call options. We can just check parameter estimates. Although at this stage we really do not need that. Here is we're gonna use default use backward elimination algorithm, and we say okay. And now we have a printout, and as we explained in the last video, first table gave us data information. Here we have 4 variables and label of each variable. And secondly, we have convergence information, and the model converged after one iteration. And then we have the count table, which have observed count and estimated count. Since we are running a saturated model, the observed counts are equal to the expected count. So all residuals are 0. Also, as a result, we cannot calculate Pearson chi-square value and likelihood chi-square ratio as well. Then we have this k-way and higher order effects. The top part of this table gave us a sense of, for example, if k equal to 3, that would mean that if we remove the third order, if we remove third order terms and fourth order terms, what's going to happen to the expected frequency? As you can see, that the p-value is very small. That means that if you remove third order terms and fourth order terms altogether, that would lead to the expected frequencies very different from the observed frequency. So you cannot do that. Okay. When k equal to 1, that means that if you remove the first order term, second order term, third, fourth order terms altogether, what's going to happen? Again, p-value is very small, so you cannot remove the terms of first and second, the third and the fourth order all together, and that would significantly alter the pattern of frequency count in the contingency table. You cannot remove the second order, and the third order, and the fourth order altogether because that would also lead to a very small r, the p-value. But you can remove fourth order by itself because the highest order term in the model is fourth order. So if you remove that terms, you got the p-values very large that will not significantly alter the frequency distribution in the contingency table. And so this is the top part of this table. Bottom part of the table is so if just eliminate this the terms of one order itself, what's going to happen? For example, if k equal to 1, that means that if you only remove terms of the first order, and what's going to happen? Again, p-value is very small. If only you remove second order terms, what's going to happen? Again, p-value is very small. So you cannot eliminate each of the first order, second order, third order by themselves either, but you can eliminate the fourth order term by itself. Okay. Next one, you see the parameter estimate table will come back to deal with the parameter estimate table later on. And then we come to a table that show the process of elimination of different terms through backward elimination algorithm. And the model enter the first into the zero steps by including the fourth order terms. And this is so-called a generating class within SPSS. And it turned out that this at the end of this zero step, this term is removed. After you remove this fourth order term, you realize the p-value is very, very large. That means that after you remove the fourth order interaction term, the expected frequency is pretty much still same as the observed frequency distribution. Okay, then we enter the next step, and after you remove the fourth order terms, you have this four third order term remain. Three interaction effect terms remain. Class sex age, class sex survived, class age survived, and sex age survived. And it turns out that one of the third order terms can be removed. You can see if you remove sex, age, and survived, the p-value is very large, and that will not significantly alter the pattern of a frequency distribution in the contingency table. Okay, so we can remove this third order term, but we cannot remove the other three first order terms because the p-values are very small. Okay. Then we enter, after we removed this third order term, we enter the next step. In the next step, we begin with three third order interaction terms, and it turned out that none of them can be eliminated because all of them would result in a very small p-value. And at the end of the step number 2, we realized that the best model is the model that contains these three third order interaction effect terms. And finally, we have a we have this the goodness of fit test that shows that for this particular model that contain these three third order interaction effect generating class, and this the chi-square value is very large. Chi-square value is 1.728. That lead to a p-value is very large, and the expected cell counts are not significantly different from observed counts. So we can use this model. Now let's just go to run this model. We go to analyze log linear general log linear model we select all four variables into the window of factors, and we go to create other model. We go select build terms. And for interaction terms, we know that the best model involves three third order interaction terms, all involve a class. So let's define these three interaction, three third order interaction terms. Okay. Class, sex, age, put it in class, sex, survived, class, age, survived. So these are the three third order interaction terms we need. All involve a class in it. Then we're gonna follow the hierarchical model principle. Let's also enter each of the six second order interaction terms. The class sex, class age, class survived, sex age, sex survived, and age survived. Okay, survived. Now we also enter all main effect terms. Okay, we enter all of them. Okay. So this is model we're going to use. Okay, and they continue. Let's see options. So we definitely are going to use estimates. Okay, because we try to explain how to work with those estimates and what they actually mean. And continue. And okay, so now we have the printout. So we have the data information table. We have a convergence information model converged after 20 iteration and goodness of fit test we thought early on. Now we come to two very important table. Cell counts table, which give us observed and expected counts. Also, we have the parameter estimates count. Now let's export these two tables as an Excel spreadsheet so that we can work on those tables. Okay, let's right-click on each table and export. That would allow you to save these two tables as Excel spreadsheet. You can choose here the type of a file. Could it be Word file? Could it be Excel spreadsheet? You can choose Excel spreadsheet to save them. Already did that early on. So now we can just move to these two Excel spreadsheet to work on those tables. Okay. Now let's take out these. Now, okay, this is a table that shows the cell counts, observed counts, and expected counts. Okay, so I have you can really see that for each variables, class 1, 2, 3, 4, and sex 1, 2 for the correspond to the first class, and age correspond to each of class in the first class. Also survived that correspond to age groups, sex groups, and within the first class. Same for the second class, third class, and crews. Okay. Now let's similar to what we did in previous video. Let's first build some partial contingency table that shows the relationship between survived and sex for different level of class. And since our model involved the third order interaction terms, therefore our partial table will reflect the relationship among three variables. Okay. Now let's build this survived. So one variable we'd like to look at is survived. For survived variables, we know that there are two levels. Okay, one is no, not survived. Another is yes. Okay, we also like to look at the sex of passengers. Okay, oh, let's have some sex of passengers. Okay, and here we have two levels. We have a male, one level, and a female, second level. Let's first build this for first class passengers. So we need to fill out uh, these cells. Okay, these cells. Okay. So we call this. We need to find out the expected counts for uh, for this table. Expected. Okay. So we need to fill out these 4 cells. Okay. Let's first look at first class male who did not survive. Okay. Now let's look at first class male is first level. Okay. Who did not survive? This one did not survive. And for each of these cases, we have male who did not survive and female who did not survive. Among the male, there's also child and adult. So let's first look at this. First class male age child who did not survive. So this. So this cell indicate first class male child who did not survive. Also, we have first class male adult is level 2 of age, and survive level 1 who did not survive is this number. Okay. So what these 2 cells tell us, the first class male who did not survive, let's put that in. So that is G4 plus G6. I'm sorry, G4 plus G4 plus G6. Okay, G4 plus G6. Let's reduce the number of decimals. Okay, make that mean 0. And then we do the same thing to find the female. Female who in the first class did not survive. Okay, the female here, the first class, sex female, and age child who not survive. Female age 2 adult and did not survive. So that is here. This is a female who are child who did not survive, and female who are adult who did not survive. These 2 cells, I put them in. They are G8 plus G10. So that's this many people, this many female who did not survive. Okay, that's 0. Okay. Now let's move on to look at this cell. This cell is for male from first class who survived. First class male, sex category 1, and age child survived, and it's 2. So this is cell we need to go. Okay. So this level also male adult also survived for this one. You can see first class, sex level 1, and age level 1 male, adult, and survived level 1 level 2. So this is here these 2 cells. So these are G5 plus G7. Okay, this many survived. Then we do the same thing for female. This cell. Female who are female is from first class, second level of sex and age child. This one also age adult who survived. Then put in blue. Okay, these 2 cells. So let's put them in. Here we type in they are G9 plus G11. So now we did this partial contingency table. We call it a partial because this contingency table is between survived and the sex only for the first class passengers. Okay, and here we are going to do the same thing to build a partial continuity table for the third class passenger. So let's make a comparison. Like the third class passengers. Okay, let's put it here. Okay, let's put it here. We change that to third class. Third class. Third class, and we change those values. Get rid of them, and we know that we need to fill out these cells. Okay, now let's look for third class male who did not survive. Here, third class male child who did not survive is this. Okay, that is one value here, and third class male who are adult who did not survive this value. So that are these two cells. Put them together, we have a G20 plus G22. Do the same thing for female. So let's say the third class female here, and the child, and not survived. Okay, this value. Okay. So that's then third class female adult who is not survived this value. Okay. So that gave us G24 plus G26. So these two values. Then third class male who survived. Third class male who survived with two values here. So child and adult. Okay. So that's for child and for adult. Okay. Now we put in this value here, so which is G20. G20 plus G22. 22. Wait. G21, 23. Okay, no. G21, 23. 23. Okay. Then we do the same for female. Female who are the third class passengers, female here, who survived too for survival, and for both child and adult. So this for child, and this for adult. Okay, that's blue. So let's put these two values in. So we have G25 plus G27. So now we have a two partial contingency table built for one is for first class passengers, another is for third class passenger. Let's do the same thing as we did in the last video. Let's calculate odds ratio and log odds ratio. Do same for both tables. Odds we know is simply the ratio between, for male is between non-survival versus survival, and also for female non-survival versus survival. Okay, let's do this. So for male odds is a P5 divided by P6. Okay, P6 is a 1.9. We do the same. We copy this formula to for female. Okay, so 0.028. Okay, now odds ratio is simply the ratio between these two odds. So let's odds ratio for male is P7 divided by odds ratio P7 divided by odds of female, which is Q7. So the odds ratio is 67.018, 0.89. Okay. Now let's find out the log odds ratio. Okay, log odds ratio, and go to the function here. Let's find natural log here. and we want to find the natural log for odds ratio. That's a log odds ratio, 4.206. Okay, let's do the same for the second table. Let's copy this formula for the second table. That's why I prefer to use Excel spreadsheet that you can copy formulas across the spreadsheet and make the calculation very convenient. Now I like to do one more thing and do two things to show some important clues so that we can later on interpret the parameters of linear model. Now I'd like to find out one thing between the two partial tables. I'd like to find out one thing which I call confusingly ratio of odds ratios. Ratio of odds ratios is simply the ratio between these two values. See, this is odds ratio from the first class passengers, and this is odds ratio from the third class passengers. I'd like to find out the ratio between the two. Let's find out the ratio between the two. The ratio between two is simply this value divided by this value, or the other way around. You could use this value divided by this value. Either way, okay. Let's just use this value divided by this value. Okay, so that's a ratio of odds ratios is P8 divided by P, this value, 20. P20. So the ratio of odds ratio is 16.477. Now I'd like to do, let's do this. I'd like to find out the log of ratio of odds ratios. It's really confusing, huh? It's really confusing. So which is simply the log of this value. Which is simply the log of this value. Log ratio of odds ratios. Okay, let's just find out the log of this value. Okay. Natural log, we find out log of this value, which is 2.8001. One last trick to play. I'd like to find out the difference between this value and this value. See, this value, see, the difference between this value is log of the ratio from this table. This value is the log of the ratio from this table. Now, I'd like to find out the difference between them. Difference between log odds ratio. Difference between log odds ratios. Okay. In two tables. Okay, that this minus this. Okay, let's see. It's P9 minus P21. Well, what is that? Now you can see that's the difference between log ratio. Okay, that's a typo. The difference between log odds ratios is exactly the same as log ratio of odds ratios. So now this is values that eventually we proved we can establish the relationship between the parameter estimate from a log linear model and the contingency table. Now let's first important thing is that what do we mean by ratio of odds ratio? Odds ratio from one table, so odds ratio, as we explained last time, from this table tell us that the male, the death of a male, the odds of death of a male passengers is 0, it's 67 times the odds of male, female passengers for class, for first class passenger. And this odds ratio for the second table for third class passengers is, it tells us that the death of a male passengers is 4 times the death odds of female passenger in third class. Again, let me recap this. This odds ratio tells us that odds of death for male passengers from first class is 67 times the odds of female passengers. And here this odds ratio tells us that the odds of death of male passengers is 4 times odds of death for female passengers from third class. Now, if you find the ratio between the two, that's going to be this. This tells us that the odds ratio, the death of odds ratio from first class passengers is 14 times the odds ratio of death for male from third class passengers. So that's actually the meaning. That's actually the meaning of ratio of odds ratio. You know, the odds ratio is something that deal with between two variables. Ratio of odds ratio is something that deal with a relationship between three variables. So you can really see after you control for the class of different passengers, so you can really find the relationship among three variables. You find relationship in between survive and sex, also between different classes of passengers. That's exactly what the ratio of odds ratio tells us. So that really means that for the first class passengers, male has a lot more chance to die than third class passengers. So if this value is larger than 1, that really tells us the odds of death for male passengers is higher than the odds of death for male passengers in the third class passenger. So you can really see that the ratio or odds ratio provide important clues regarding the relationship among three variables. And this value can be derived from log ratio or odds ratios, because if you know this value, so if you know the log ratio of odds ratios, you can simply take you can simply take an exponential of this log ratio of odds ratios to get ratio of odds ratio. For example, for this value, let's go to find exponential. Exponential. We like to find out exponential of this value. Okay, let's see what value is that. That exactly give us the ratio of odds ratios. Our ratio of odds ratio gave us the relationship among three variables from a continuity table. Now let's go to see the parameter estimate table from a log linear model. Let's see what we can get from there. Okay, let's copy something over to that page 2. Let's copy this part of this continuity table to the parameter estimate table. Okay, here's the parameter estimate table. Let's copy it to here. But we changed expected count to parameters. We get rid of those values. Now we're going to fill in the parameter estimate. We do the same thing for the second table. Let's go back to copy the second table for third class passengers. Okay, third class passengers. Okay, so now let's go to third class passengers. Let's go to here. Copy it here, and again, we want the parameter estimate rather than expected count. Okay, and we need to replace those value with the parameter estimate. Okay. Okay. Now, well, let's do one more thing. The first class has three levels. Okay. One level is so first class has four levels. First class is level one, and survive has two levels. No is first level, and yes is second level. Let's label those levels with numbers too, and sex at two levels. You have male at first level and female at second level. Okay. Let's do the same for the third class. Third class, in terms of class, is third level. Okay. And to survive, you have this no at first level, yes and second level, sex male at first level, and female at second level. Okay. Now we're going to fill out these forms with these tables with parameters. Okay, let's first look at the first table. We try to find out those parameters. Okay, let's see. First class 1, sex, refer this field. Class 1, sex 1, survive 1. Okay, let's go find out parameters. Class 1, sex 1, survive 1. Class 1, sex 1, and survive 1 is this value. Okay, 0.728. Copy this value to this cell. This is the parameter for this cell. Okay. Now we look at class 1, sex 2, survive 1. Class 1, sex 2, survive 1. Class 1, sex 2, survive 1. This value. Okay. Class 1, sex 2, survive 1. Okay. Copy to this cell. Okay, copy to this cell. Okay. See that? Then we can do the next one. Then for this cell we have class 1, sex 1, survive 2. Okay. Survive 2. Class 1, sex 1, survive 2. Class 1, sex 1, survive 2 is 0. Okay, let's type in 0. And the last one is class 1, sex 2, survive 2. Class 1, sex 2, survive 2. Class 1, sex 2, survive 2, also 0. Also 0. Okay, now let's type in 0. And we do the same for the second table. Third class. Class 3, sex 1, survive 1. Okay. Class 3, sex 1, survive 1. Class 3, sex 1, survive 1. This. Okay. Class 3, sex 1, survive 1. Okay. So this is this value going to here. Okay. Then class 3, sex 2, survive 1. Class 3, sex 2, so class 3, sex 2, survive 1. This. Okay. Class 3, sex 2, survive 1. Okay, that's the right level here. The next one is class 3, survive sex 1, survive 2. Okay. Class 3, sex 1, survive 2. Class 3, sex 1, survive 2, 0. And finally, class 3, sex 2, survive 2. Class 3, 6 3 6 2 survive 2 here class 3 6 2 survive 2 0. Okay, so now we fill out these two tables here, and also we're going to do what we did before in the last video. So we're going to add up these two values and minus these two values. Okay, let's see what we got here. Okay, and here, let's see. So we're going to deal with these four values here in both tables. In both tables. So this plus this minus this minus this. Okay, let's do that. So it's a K7 plus L8 and minus K8 minus L7. So it's this plus this minus this minus this. Okay, so we have this value. Okay, we do the same for this table. Okay, we do this, copy this formula over. So we have these two values. Okay, and what they are? Well, as we explained in the last video, this value is a combination of a parameter for these four cells. We call it log odds ratio of this table. So this value is log odds ratio from this table, and this value is log odds ratio from this table. And since we are dealing with three variables, we're not interested in log odds ratio themselves. We're interested in the difference between two log odds ratios from these two tables. You know, as we did here. Let's go back to the first the cell counts table. We are interested in the difference between two log odds ratios. So let's find out the difference between two log odds ratios. Come to this. We'll find out the difference between this value and this value. The difference between two log odds ratios. Let's copy these words over. Difference between two log odds ratios here. Simply we use this log odds ratio minus this log odds ratios. Okay, so that's okay. That is K9 minus K15. 2.89. Let's compare this value with. So this is a value. Compare this value with value that we obtained from partial contingency table. So here, 2.8 is 2.8019 from the partial contingency table, and from the parameter we have 2.898. So it's not exactly the same. But now, if you notice here that we look at for this parameter, class 3 sex 2 survival 1. This value class 3 sex 2 survival 1. Okay, this value here. Class 3 sex 2 survival 1. This value. 0.27, the p-value is 0.147. In other words, this value is not significantly different from 0 at 5% level. So in this table, what you should do here is to, it is 0. Let's get rid of it. Let's type in 0. Okay. When you type in 0, the difference between two log odds ratio become 2.68. Let's see, 2.68 compared with 2.80 is still not exactly the same. But here you can look at in the parameter estimate table, the table only, so that is theoretically these two values should be exactly the same. Should be the same, or at least similar. But in our case, there's some discrepancies, but that discrepancy does not take away from the fact that these two values are similar in magnitude. So this value should be the same as this value. Okay. Therefore, they should reflect the same information. That takes us to an important point that that is the meaning of the parameter estimate from a log linear model is to allow us to calculate the log odds ratio and the difference between log odds ratios. For a log linear model that has only three third order interaction effect terms, here this is very critical. We like to find out what is the difference between log odds ratio between different partial tables, because the difference between log odds ratio tell us information about ratio of odds ratio. We like to find out the odds ratio between different partial table, how different they are. Are they larger than one? Are they smaller than one? So therefore, by interpreting the parameter estimates of log linear model, what we actually get is this, the difference between log odds ratio, which eventually take us to the ratio of odds ratio, which is at the heart of interpreting uh, the, the log linear model. From this information, we take exponential, we get information of ratio of odds ratio, and this tells us that for first class passengers, the odds ratio of passenger deaths, male passenger deaths, is 16 times the odds ratio of male passenger deaths for the third class passengers. And that is exactly the information we would like to get from the log linear analysis. And the parameters of the log linear model allow us to get information of difference between log odds ratios, therefore eventually take us to, if you take exponential of this difference between log odds ratios, that would give us ratio of odds ratios that tell us the relationship among three categorical variables. Okay. I hope this helped. I see you next time. Goodbye.